All right, 1.5 continued. We're going to continue with the absolute value function. F of x equals the absolute value of x. So again, I'm going to pick some x values here. And I'm going to plug them into the function to get my y values. Now remember, when you take the absolute value number, it's always going to come out positive because absolute value tells us the distance that number is from 0, and distance is always positive. So the absolute value of negative 2 is 2. Absolute value of negative 1 is 1. Of 0 is 0. 1 is 1. 2 is 2. And so we're going to graph this. And it makes a V-shaped. So for our domain, does our graph keep going to the left? It does. Keep going to the right? It does. Any jumps, holes, or gaps in between? There are not. So therefore, domain is negative infinity to infinity. Now range, does the graph keep going down? It does not. The lowest y value is right there at that vertex when y is 0. Does it keep going up? It does. So we already said there's no holes, gaps, or anything like that. So we know it's going to be 0 to infinity. And the zeros included, so make sure you put a bracket. And then the limit, as x goes to negative infinity, as we go to the left, our y values are going up, and they're going to keep going up to positive infinity. As x goes to positive infinity, so as we go to the right, again, our y values are going up, and so they're going to keep going up to positive infinity. Intercepts, I have an x and y intercept at 0, 0. And then the other, so let's go through our list. So increasing, decreasing, or constant. Well, we can see as we read this from left to right, the first part of our graph is decreasing, the second part of it's going to be increasing. So therefore we know it's decreasing from negative infinity up to the 0, and then it switches to increasing from 0 to the positive infinity. Symmetry, is it even, odd? This function is even because we can see that it is symmetric to the y-axis. Absolute value is not considered bounded, though we could say it's bounded below because it doesn't keep going. No local extrema. Let's go ahead and let's put that it's bounded below. Let's go ahead and include that. No local extrema because that's not a valley, that's a sharp curve, okay? Remember, local extrema are the valleys and the hilltops. That's a sharp curve down there, so it's not a valley. And we talked about end behavior. And is this continuous? It is continuous. All right. Moving on to the cubic function. Cube root, excuse me. It says if f of x is equal to the cube root of x. So we're going to build ourselves a table. But because this is a root function, I'm not going to use my normal negative 2 to 2. I'm going to pick numbers that I can take the cube root of. And so I'm going to use negative 8, negative 1, 0, 1, and 8. So the cube root of negative 8 is negative 2. Of negative 1 is negative 1. 0 is 0. 1 is 1. And the cube root of 8 is 2. Now, we haven't talked about it yet, but a radical and an exponent, remember, are inverses of each other. And inverses means you switch the x and y. So if you look back, when we did that cubic function earlier in the other video, we had this for our table. Okay, so the cube root is just the inverse of it, so we just switch the x and y's. I didn't mention it either in the other video when we did the square root. Square root and x squared are inverses. So again, their tables were just switch x and y. But because it is an even number, when I did the square root, I had to take out all the negative x values. So we had to limit it. But a cube root, an odd root, we don't have to do that to. All right, so we got our points there. Let's go ahead and graph them. And then let's look at our domain. Keeps going to the left. So it keeps going to the right. No holes, gaps, jumps, or anything like that. So negative infinity to infinity. This graph does keep going down for our range. It's just decreasing at a decreasing rate. It's still going to go down. It's just going down slower and slower. Keeps going up. No holes, gaps, or anything like that. So negative infinity to infinity from our range. Now my limit, or the end behavior. The limit as x approaches negative infinity. So as we go to the left here, our graph is still going to go down. It's just going down very slowly. And it's going to keep going down until it gets to negative infinity. And vice versa, on the limit as x goes to positive infinity, our graph is just slowly going up, but it's still going up. So it's going to keep going up to positive infinity. Intercepts, we have an x-intercept and a y-intercept. Both of them are at 0, 0. And then the other. Is it increasing, decreasing, or constant? This graph is increasing over the entire domain. So from negative infinity to infinity, it changes the speed at which it's increasing, but it's still increasing. Symmetry. This graph is symmetric to the origin, which means it is odd. This graph is not bounded. It keeps going up and down. There's no local extrema. There's no asymptotes. And is it continuous? It is continuous. So that's our cube root. All right, let's keep going then. So the exponential function, they use f of x equals e to the x. Just know that that base, that e, could be any number, okay? They chose e. If I was going to graph this, well, I'm going to graph this, but if it was a number other than e, because e is an irrational number. It's like pi. It's a number that's just going to keep going and going and going. But if I had any other base, if I had a base of 2 or a base of 3, something like that, then I could use a parent table as well. And so I would use these values here. So what we would see here is we'll have e to the negative 2, e to the negative 1. This would be e to the 0. And remember, your exponent rule says 0 exponent. The answer is 1. Then we would have e to the first, and we would have e to the second. All right, so when I go to graph these, the thing is with exponential functions, you're going to have a horizontal asymptote at y equals 0. And we know we've got this point 0, 1. And then e is approximately 2 point something. So when we have this 1 e to the first, we know it's going to have a point that's somewhere up in here, okay? So my graph is going to look like this. So that's what the graph of an exponential function is going to look like, the parent one. So our domain, it keeps going to the left, it keeps going to the right. There's no holes, jumps, or gaps, so therefore it's negative infinity to infinity. Our range, it does not keep going down. Its lowest value is the number that's right above 0. And that's not 1, it's just whatever number is right above 0. It's just not going to touch that horizontal asymptote. So therefore, we're going to start at 0, and it does keep going up, so we're going to go up to infinity. Now, it's not going to equal the 0, so we're going to make sure we put a parenthesis there for the at the 0. All right, the limit as x goes towards negative infinity. So as we're going to the left, that graph is going to go towards that horizontal asymptote. It's not going to cross it, but it's going to get super duper close to it. So the f of x, the limit as x goes to negative infinity of f of x is 0. Then the limit as x goes towards positive infinity, well, as we go to the right, we can see that we're just keep going up and up and up, and we keep going up till we get to positive infinity. Intercepts, there is no x-intercept, because that is that horizontal asymptote, but there is a y-intercept, and that y-intercept is at 0, 1. And so when we go through our graph, we can see, let's see, is it increasing, decreasing, or constant? It is increasing across the entire domain. Symmetry, it has no symmetry. It is bounded. It's bounded below. No local extrema. It has a horizontal asymptote at y equals 0. And is it continuous? It is continuous. All right, then we have a log function. A log function is the inverse of an exponential function. So that means that we would again just switch their x and y's. So if I needed points on this one, the one point you would definitely have on this graph then is going to be the point 1, 0, because every exponential function has the point 0, 1. All right, so when I go to graph this one, and also I didn't write it at the bottom here, I'm going to now. Remember we had that horizontal asymptote at y equals 0? Well, if x and y switch, we're going to have a vertical asymptote at x equals 0. So we got this vertical asymptote here. And we got the point 1, 0. And so our graph is going to look something like this. So when I do my domain, does my graph keep going to the left? No, it's going towards that vertical asymptote that's at 0 though. But does it keep going to the right? Yes. So we're going to go from 0 to positive infinity, but the 0 is not included because it's a vertical asymptote. And remember, it'll never cross a vertical asymptote. Your range, does your graph keep going down? Yes. Does your graph keep going up? Yes. No holes, no gaps, nothing in between. So negative infinity to infinity. Now notice again, they put the limit as x is going towards 0. So as our x value goes towards 0, what's happening to those y values? They're going down, and they're going to keep going down to negative infinity. The limit as x goes towards positive infinity, so as my x's get bigger, my graph keeps going up, and it's going to go up to positive infinity. Intercepts, there is no x-intercept, that's the vertical asymptote. And the y-intercept is at that point 1, 0. I'm sorry, I said that backwards. Up. Sorry. Totally said that backwards. The x-intercept is at the 1, 0. And the y-intercept is that vertical asymptote, so there is none. Sorry about that. All right, and then the other stuff. Let's go back through it. Domain range. We talked about the x-intercepts, the y-intercepts. Increasing, decreasing, or constant. This graph is increasing across its entire domain. So negative infinity to infinity. Symmetry. There's no symmetry. Boundedness. No boundedness. It keeps going up and down. No local extrema. We do have an asymptote. We have a vertical asymptote at x equals 0. And is this graph continuous? It is continuous. All right. And then just a couple more functions that we don't see very often, but this way you've been exposed to them, okay? The greatest integer function, we talked about this earlier, it looks like a step function. It is actually the same as one of the functions we looked at before. So the greatest integer function is the one in which we're going to round up. So it's like our Signum function we talked about before. I'm sorry, I said ceiling. It's the floor function. I think I mentioned it when we talked about it before. These are supposed to be open circles, my little bit bigger ones. Sorry, some of them it doesn't quite look open. See if I can fix that a little bit here. Put at least a small little hole in there. All right, I think they all got a small piece. All right, so it looked like that. And so our domain is negative infinity to infinity. So let's talk about that. So if I look, I would keep going, okay? So I only stopped because I ran out of lines. But when I get to like this x value here, it's open here, but it's closed there, so it's included. And then it goes all the way to here where it's open, but it's closed right there, so it's included as well. So every x value is going to be included. Now for my range, I've got all these gaps going on, right? It does keep going down, and it does keep going up, but we've got all these gaps to think about. So the only thing we have lines at are the actual integers, the actual, like what we think of as whole numbers, positive and negative, which are called integers. So the range is just going to be your set of integers. The limit as f of x goes to negative infinity, as x goes to negative infinity, so as we keep going to the left, excuse me, my graph's going to keep going down till y is negative infinity. As we go to the right, our graph is going to keep going up, and it's going to keep going up till it gets to positive infinity. X-intercepts, we do have an x-intercept. So our x-intercept is actually the interval from 0 up to, but not including the 1. And we do have a y-intercept. It's going to be at 0, 0. All right, and then the other. So let's see. Increasing, decreasing, or constant. It's constant between the intervals. Integers. Constant between integers. Just write it out in words. It's easier than trying to use notation. Symmetry. Be careful on this one, because if I take this point right here and I reflect it across the x and I reflect it across the y, there's a point that lies there, but I took an open point and it's a closed point. So there's no symmetry. So it's not even nor odd. It's not bounded, no local extrema, no asymptotes. And is it continuous? No, it's not. This is discontinuous. All right, and then the last one we're going to look at is the Signum function. Okay, and it's a piecewise function. So we're going to take f of x is equal to the absolute value of x over x when x is any number other than 0, and when it's 0, it's just going to be 0. So we can think about this. If I do a table to just kind of help us think, okay? So I'm going to pick my normal x values. I'm doing it a little different because it is piecewise, but we already know because it told us right here when x is 0, it's 0, right? So we know that's going to be a 0. Now this applies to everything else. So if I take negative 2, the absolute value of it, and divide it by negative 2, I'm going to get, well, absolute value of negative 2 divided by negative 2 is 2 over negative 2, which is negative 1. And if I take the negative 1, the absolute value of it over negative 1, I get 1 over negative 1, which is also negative 1. But when I take the absolute value of positive 1 over 1, I get 1 over 1, which is 1. And the absolute value of 2 over 2 is 2 over 2, which is also 1. So when I graph this, what's going to happen is at the 0, 0, we're going to have a point. At negative 2, we see we're at negative 1. At negative 1, we're at negative 1. All of these, we're going to be down at negative 1 until we get to the 0. All right, so I'm going to put an open circle there, and my graph will look like this. And then you had the 0.11, the 0.21. It says the same thing. Even if I pick 0.5, it's, oops, I'm up at 2. Sorry. Try that again. Now I change colors. There we go. There's those points. Sorry about that. So even if I pick 0.5, when I plug it in, it's going to give me 1. If I pick 0.1, it's going to give me 1. So everything back up to, but not including that 0, would give me a 1. And so this is what the Signum function looks like. It's a step function as well. You can see the steps there. So when we talk about our domain, does it keep going to the left? It does. Keeps going to the right? It does. It does have some jumps here, but as far as the x's involved, all the x's are included, because right there where I just put that arrow, the x is included at the 0, 0. So all the x values are included, so negative infinity to infinity. The range, it does not keep going down. It does not keep going up. It's only going to use the integers negative 1, 0, and 1. Then our limit, as x goes towards negative infinity, so as we keep going to the left, we're just going to stay at that negative 1. And as we keep going to the right, it's just going to stay at that positive 1. And then your intercepts, you have an x and a y intercept. Both of them are at 0, 0. And then let's see, let's go back to our list. And so is it increasing, decreasing, or constant? It is constant. From negative infinity to 0, and then from 0 to infinity. But there's a break in them, so we got to put a break. Let's see, symmetry. It is odd, which means it's symmetric to the origin. It is bounded. It's bounded above and below, so we can just say bounded, because remember, bounded by itself stands for both. No local extrema, no asymptotes, and it is discontinuous. All right, and so the next 6 functions that it talks about here are trig functions, and we actually don't cover trig until the second semester. So if I go over it now, you're going to forget it by then anyways. So I'm just going to wait, and we will cover those trig functions when we actually get to graphing in the trig unit. All right, so this is the end of the 1.5 that we're going to cover.